Welcome again, once again. Thanks for coming back for another installment. Let's do some calculations, shall we? They're pretty simple when it comes right down to it. Once you get the hang of it, we're just wondering what percent or what fraction, what amount of a particular compound is a particular element. So all you have to do is know what the numbers are. By that I mean, if you knew how much carbon there was, how much nitrogen, how much hydrogen, how much oxygen in a particular formula, then it's fairly simple to break it down into what fraction of the total is one particular element. So let's take an addictive, nasty drug, nicotine, and the formula evidently is C10H14N2, and I can tell that from the vertices of the polygons. That's a carbon, 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 that's a nitrogen. Carbon, 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 nitrogen. Did I say carbon? I did, I think. In any case, we don't mention some hydrogens here, also some double bonding. It'd be fun to play around with organic chemistry and make sure you know the structure of that thing. But in any case, if it's C10H14N2, then I look at the periodic table and look up the grams per mole, AMU, average atomic weights for those elements, and that adds up to 162.2-ish. We've done that for a long time now. But my new twist is, how much of that 162.23 is carbon? Well, there were 10 carbons, and each one weighs 12. So 12 times 10 is about 120.1. Divided by this gives me a decimal. Change it to a percent. So in the nicotine molecule, its mass, by mass, 74-ish% carbon. And 14 hydrogens. Each hydrogen weighs 1.008-ish. And that comes out to close to 14 divided by 162.3, and about 8% hydrogen. Percents are out of 100, so I move the decimal 2 places. Nitrogen must be the remainder, so by that I mean, if I added up this plus this and subtracted from 100, I should find 17.27, or you can just divide 2 nitrogens by the total mass. Interesting. Now this is called the molecular formula. It's the formula for the elements in the compound. But you know what? 10 and 14... did I make a mistake? I made a mistake. That's not a 7, that's a 2. Hello. Alright, let me go fix that. Is that true? Yeah, that's true. That's, sorry I'm flashing through these pages. You're probably getting dizzy. That is a 2 right there. I'll fix that on the PDF. That's a 2. That's a 2. But you know what? The 10... No, I gotta fix that now or that's gonna bother me. Yeah, I'll be right back. Fiddlesticks. Alright, sorry about that. That was bothering me. Yes, C10H14N2. But you know what? As I was saying, that's called the molecular formula. But 10 and 14N2 all divide by 2. And as a matter of fact, in other experiments, we'll determine the empirical formula, which is just the lowest whole number ratio of carbon to hydrogen to oxygen. So if these quantities of each element are reducible, sometimes, many times in experiment, all we can tell is that lowest whole number ratio. But you'll notice that both this and this give the relative percentages that are the same. So you'll have to fiddle with that a little bit. Empirical versus molecular. Sometimes if we find them empirical, we can work back upwards and get the molecular. Or the molecular, but otherwise maybe not. Alright, a pure organic compound found to have 49% carbon, 5% hydrogen, 28.8% nitrogen, 16.48% oxygen. The total molar mass is described by 4 grams equals 0.02059 moles. What's the empirical and molecular formulae for the compound? Plural of formula, perhaps. Alright, I don't know. Let me take... Oh, here's a trick. If you're given percents, it's nice to think about a 100-gram sample. You say, well, what if you don't have a 100-gram sample? Well, the answer is everything else is proportional because percents are out of 100 anyway. So if I had 100 grams, this would go to grams, to grams, to grams, to grams, the same digits. 16.48% would be 16.48 grams of oxygen in that sample. Alright, that's the first trick. The second trick is to go ahead and change all the grams to moles. This is the way I do it anyway. So I think grams to moles, grams to moles, grams to moles, molar mass on the periodic table, and each of them changed to moles. So no big deal, whatever. But now here's another big deal. The last trick, almost the last trick, usually the last trick, is to compare this mole and this mole and this mole and this mole quantity to the smallest mole quantity, which is oxygen. Now here we're assuming that that oxygen is indeed just one particle, one atom of oxygen in the empirical formula. That may or may not be true, and if it's not true, we'll get our last twist, but in this particular problem, I think that's going to be it. So divide it by itself, and divide this by 1.03, divide this by 1.03, divide this by 103 moles, and I find usually integers. If not, we'll have to fiddle with it, but usually integers. So that means 4 carbons, 5 hydrogens, 2 nitrogens, and 1 oxygen in this compound. So maybe. Well, definitely that's the empirical formula, but what's the molecular formula? And the answer is, let's look at that other data that was given to us in this question. And that would be that 4 grams equals 0.02059 moles. That divides in grams per mole to give me my molar mass. By the way, this was determined in a different experiment, maybe a freezing point depression experiment, very famous. You'll learn about it. Probably when we talk about colligative properties next semester. But anyways, that's 194-ish grams per mole. Grams per mole. That's the definition of molar mass. So if I went with my original empirical formula, C4H5N2O, that all adds up to 97 grams per mole. Question, how many of these 97 grams per mole units empirically are in the entire molecule? And the answer is 2. Or is it obvious? I don't know. Divide the empirical molar mass by the otherwise determined molar mass in a different experiment, and you'll usually find, you will find a whole number. That means take all of this times 2 to get my molecular formula. And interesting, isn't it, that the molecular formula that I was alluding to so secretively is actually caffeine, which is some of our favorite drinks in the morning time. You can count them up: carbon, 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 4 nitrogens, and 2 oxygens. And there's hydrogens thrown in anywhere, maybe not. Yeah, I think that's all the hydrogens listed. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, there must be one I'm missing somewhere. Here it is. On this carbon has that extra hydrogen that's not mentioned. All right, another example. Organic substance found to have 41.39% carbon, 3.47% hydrogen, and the rest is oxygen. So what do those percentages add up to? Well, they must add up to 100%. Excuse me. So if I take this one and this one away from 100, the remainder must be oxygen. That was mentioned in my question. Oxygen, common element, hydrocarbons. And that comes out to, change grams to moles, grams to moles, grams to moles. I went ahead and just said, well, take a 100-gram sample, changes the percents right away to moles, or percents to grams, change the grams to moles. And now just like before, but wait a minute, this one and this one and this one are all very close to within experimental error. That last digit is a little bit variable. So this one compared to 3.442, this one compared to 3.442, and this one compared to 3.442, comparing them all to the smallest number is very, very close to 1. But there really can't be a C1H1O1. There must be something more to it than that. For one thing, that molar mass adds up to 29. But perhaps in a different experiment, as I've been mentioning, we find the molar mass to be 15 grams is 0.129 moles. And that will come out to, 116 grams per mole. So the question is, how many of these 29s fit into the 116? And the answer is 4. So what? That means the empirical formula, C1H1O, is really 4 times bigger than that. And there's an acid, what's this acid called? Oh golly, maleic acid, I think. I have to look it up, I've forgotten. But it really does come out to that molecular formula. All right, one more, well, at least one more. This is so much fun, I could go on forever. Let's see. So composition, potassium, chromium, oxygen. We know what to do. Change the percents to grams. Assume a 100-gram sample. Change the grams to moles. Compare each mole to the smallest number, 0.681, 0.678. Oh, there it is, 0.678 moles. So, but those two are very, very close to each other. I should say this is exactly 1. I should say this is approximately 1. Yeah, it is approximately 1. 3.5. Wait a minute. How can you have 3.5 oxygen atoms? Well, you just can't round that off so simply. Usually our numbers come to within one digit of the whole number. If it doesn't work, sometimes you'll get like 3 1/3 or 3 1/5. If that's the case, you really have to take that and multiply everything times a constant term. Let's see, another name for 3 halves is, oh golly, what is that? 7 halves? So what could I possibly multiply each of those terms by to get an integer quantity? Multiply this times 2. Times 2. Times 2. Yeah, 7 halves times 2 is, 7. Duh. And so the formula really is K2Cr2O7. That's called potassium dichromate. That dichromate's a famous oxidizing agent. Here's a different way to do these problems if you care. I'm almost done. Last one, I promise. Scout's honor. If a compound has a molecular weight of 70.1 grams per mole, that's determined probably from a different experiment. Then in, say, perhaps a combustion analysis, which I'll cover in a future video, I find the carbons and hydrogens to come out to these relative masses. Well, this is a good trick. It's interesting. The total mass is 70.1 grams per mole, and my percentage was 85.63% carbon, 14.37% hydrogen. So this is believable. Then check out what I do over here. I say take this and do one more conversion with it, and that is 12.01 grams per mole of carbon, and lo and behold, you get an integer, or something close to an integer, and that's close to 5, and this is close to 10, and so you know what? My molecular formula, based on the total molar mass, C5H10, C5H10, which also divides down to divide both by 5. The empirical formula for that C5H10 would be C1H2. Oh yeah. Well, see you in class, guys. Thanks seriously for watching, and yeah, catch you soon.